Welcome back, everybody. We're going to be jumping into our next unit, which really starts to dive deeper into some pretty specific types of functions. I love how our materials are structured and their progression throughout the year. So our first chapter was really about all the different types of functions that are out there. It's a bit like how scientists would study the animal kingdom. And we're moving into studying some very specific animals themselves. The first target is about absolute values, and the second target in this unit is about quadratics. And we're going to be able to compare them. In a weird way, it's kind of like when you were a kid and some of the first animals that you were familiar with probably were cats and dogs. They behave a little bit nicer, they're more common, and that's what this chapter is. It's introducing us to the cats and the dogs of the function world. So let's dive right in and let's look at our first idea. So this target says that we hope that you can describe, graph, and write equations for absolute value functions. And we have to start off with the parent function. So number one is asking us to fill out this table for f of x. And if you read the prompt for this question, it says f of x equals the absolute value of x. That's what those bars mean. Now, if you remember from our first unit, typically equations without any transformations are called the parent equations or parent functions. And so this is the parent function for the absolute value family. If we're looking at the table, the left-hand column is all x values. And so we can essentially choose whatever x values that we want and put them in there. And then the second column over to the right is the f of x column, which, remember, f of x is just a fancy way of saying y equals. So we have an x and a y, and that's going to come up here in a minute. So usually in class I just have people shout out random numbers that we want to try. For this video, I'll start with like -5. Then maybe we can choose -3, -2. I try to choose 0 because a lot of times interesting things happen around the origin. 1, 2, 4, and maybe if we were feeling extra adventurous, 7.5. So choosing these x values is a bit like going to the buffet. You can pick whatever you want, and we have to try it to see what is going to happen with those numbers. So 7.5 is a bit like sushi. So, ooh, we're trying something new here. Decimals are perfectly fine in general. If I go ahead and put these x values in, the first is the absolute value of -5, and that's just 5. If we move down, the absolute value of -3 is just equal to 3. Plugging in -2, the absolute value of that number is 2. And then the absolute value of 0. Sometimes people pause because they wonder, can you even do that? Well, sure. The absolute value of 0 is 0. Now moving into the positives, the absolute value of 1 is just 1. The absolute value of 2 is 2. The absolute value of 4 is equal to 4. And then if I have an x value of 7.5, the absolute value of that is 7.5. So absolute values take whatever number is inside and it rips away the negative if there is one. If the number is already positive, it doesn't really care. And we're going to talk about later this common idea of what absolute values really talk about, the concept behind them. So looking at those answers, secretly we're dealing with y values. Remember, that's the column that we're in. And so if we have a y value on the right and an x value on the left, remember what x and y values come together to create. They create points. So x comma y. So all of these input and outputs are coordinates. So -5 comma 5, -3 comma 3, -2 comma 2, 0 comma 0, 1 1, 2 2, 4 4, and then the last point is 7.5 comma 7.5. If we graph those on our coordinate plane, they start to reveal the image of what an absolute value function looks like. Now, if you really studied the first unit, you should already know what shape absolute values make. They make V's, or if they're reflected, they make A's, which is convenient because A and V are the first letters in absolute value. That's how I always remember it. Now these dots are lining up in a pretty particular pattern. The slope of each arm is 1 over 1 over 1 over 1. Now technically on the left it's -1 over 1 because it's coming down. We go from left to right. And then on the right hand side it's up 1 over 1, up 1 over 1. So slope is pretty generic. Remember, parent graphs aren't that exciting, and so the slope is pretty basic here. Looking at this function, all the other absolute value graphs are going to be generated by this. They're all just babies of this original parent. You can transform them, you can manipulate them, but they all come back to this ancestor. So let's look at the second question. It asks, is an absolute value equation or the graph considered a function? Why or why not? Now, if you're in honors, we've already discussed what it means to be a function. But for my regular classes, a quick summary of what it means to be a function is that whenever you put an x value in, you're never going to get multiple y values out. So here's my analogy for what it means to be a function and why you can only have one thing producing at most one thing. Let's say that you're baking. You're going to bake cookies, and so you mix all the ingredients together that are in your recipe, and you put it on the sheet, and you put it in the oven, and you wait 20 minutes or whenever, and then when you pull the sheet out, there's a pizza on the sheet. Wouldn't that be kind of weird? And so you're wondering, well, what the heck's going on? So you do it again. Same exact ingredients, same exact recipe. You do it exactly the same. You put it on the sheet. You put it in the oven for the same amount of time, 20 minutes. And when you pull it out this time, it's cookies? How can you do that one time and get a pizza and then do it another time and get cookies? Like, how can you get two different things from the same exact process? When you're a function, that's not allowed. Like in real life, that's not allowed. And so using a particular x value, like using 4, just like in the table above, it's always going to produce 4. If I use -2, that is always going to produce +2. There is never going to be like potential multiple answers that would be correct. I can't have 2 and then -5. Like, that's like pizza and cookies. It can't happen. Now visually, it's pretty easy to spot because 2 outputs looks like 2 dots above each other on the graph. That would mean that that singular x value produced 2 outputs, pizza and cookies, and that would be bad. Graphs that typically have y values above each other, 2 outputs, they tend to go backwards over itself, and so that's something to kind of look out for. Now mathematicians have created a test to determine if it is a function. It's called the vertical line test, where you take a vertical line and you sweep it across the graph, or you scan it, in order to see if these multiple y values are setting off any alarms, because that would be bad. That would be something that's not a function. So if we look here, this is a function because it passes this vertical line test. There are no 2 y values for a singular x value. Now, kind of an interesting piece of information. The absolute value graph is this V shape for a reason. Absolute values are measuring the distance of a particular number from 0. That's why none of the answers are negative. You can't have negative distance. If I'm talking about my distance from me to another student, I would say like, oh, it's 6 feet. I'm never going to say, oh, I'm -10 feet away from you. Same thing if you're talking to your parents. You'd never say, Mom, I'm driving -30 miles to so-and-so. That just doesn't make sense, and so distance is positive. Now there's a second layer to this. The absolute values and lines are kind of related. If you look in my little example here of Desmos, I'm going to graph a line, and then I'm going to lay on top of it an absolute value graph. Okay, and these are both parents. Now on the right-hand side, they correspond. They're in the same exact spot. They have the same inputs and outputs. But on the left-hand side, it looks almost like they're a reflection, a mirror image of each other. And so if you think about taking that straight line and twisting it to be up there where the absolute value is, that reflection takes the negative values and makes them positive. And what's really cool is if we do absolute value ideas to other types of graphs. So I'm going to put a quadratic up, and this quadratic is positive and negative. And then I'll copy it, and I'm going to put absolute value bars around it to see what happens. And you can clearly see the negative part got cranked around and reflected to be positive. So absolute values talk about the distance from 0, and distance itself can't be negative. Now I'm not saying we'll never have parts of the graph that don't go negative, because there are still other transformations you can do outside of it. But when you take an absolute value of something, it takes anything and it makes it positive. So absolute values take a graph and reflect the negative portion so that it's going to become positive above the x-axis. A really cool visual that I wish I would have seen earlier in my math career. Let's look at number 4. We're going to start introducing transformations, which hopefully you feel comfortable with from the first unit, and talking about them with absolute values. So we have g of x. You can call this Gary or Gertrude or Gina, and g of x is equal to the absolute value of x plus 2 inside, and then afterwards minus 4. So those transformations, just a horizontal shift left 2, remember it's backwards, and then a vertical shift down 4. Now what is interesting is our parent graph shifting at left 2 and down 4, that vertex point is leading the way. That's what I always typically start with. Because the vertex is on the origin, stretches and compressions and things like that don't influence it. Now I know we don't have that here, so it's pretty easy to start with moving left 2 and down 4 and plotting a point here. Now what happened to the slope of our arms? Well, if the parent was 1 over 1 over 1 on both the left and the right, this kid graph has the same exact pattern. There weren't stretches or compressions or flips, reflections across the x-axis in order to change that at all. So from that new vertex point, from the new starting point, we can go 1 over 1 over 1 over 1, rise over run, and that's how we get the rest of this shape. I'd encourage you, make sure that you're graphing your things all the way across this coordinate plane. I hate when students give me like 2 points on each side and that's it. There's so much more of the graph that you would want to see. Kind of like high definition 4K, like you want the best image possible. And really for this type of a graph, it's not that hard. Now we're going to go ahead and use substitution to confirm that we actually have the right graph. Just like the table up above, it's producing that absolute value parent graph. The table is really the engine behind why we're getting that shape. And I know a lot of times we don't think about the engine of our cars if we're going from A to B, but it's important to understand how it works in case something bad happens. So you can choose any x values that you want, just like we chose any x value up in the table. So maybe for these notes I'll choose 2 and negative 4. And if we plug those into the x position, it's the absolute value of 2 plus 2, that's inside, and then minus 4 is at the end. Now we just follow the order of operations. Those bars almost act like parentheses here, and so 2 plus 2 makes 4. The absolute value of 4 is 4, and if I take 4 minus 4, I get 0 as a result. Now remember that answer is a y value, and so that y value and that initial x value come together to create a point. So this point should happen at 2, 0, and if you go to the graph and you find 2, 0, it is on this V. And so we nailed it, or at least one of those points is correct. It would be helpful if we checked maybe another spot, just in case we feel uneasy. So this is where the negative 4 comes in. If I place negative 4 in for x, negative 4 plus 2 inside of absolute values creates negative 2 inside the absolute values. The absolute value of negative 2 is positive 2, but that's not my answer because remember there's minus 4 at the very end. So 2 minus 4 is negative 2. Keep in mind that y value and that initial x value go together to make this coordinate negative 4, negative 2. So if I go left 4 and go down 2, do I end up on the graph? The answer is yes. So the reason our graph is anchored where it's at is because the algebra behind it is producing all of these points. And it helps to know kind of the secret patterns behind them. To be honest, in high school, I would just do tables and tables in order to get these shapes. I wish I would have known about these transformations left and right and up and down in order to make my life just a little bit easier. It definitely would have saved me some time. So the very last thing that I want to talk about is the domain and the range for this graph. Very important idea. Domain, if you remember, is the x values. So that's where does the graph go left and right. And if you remember from the table, I was kind of unlimited in terms of what I could choose. I chose 7.5. I chose negative 4 for this problem. You can choose almost anything. And visually, that shows up by going left forever and going right forever. It never stops. There's no boundary in terms of x values. So the domain here is from negative infinity to positive infinity. The range, or the output, I'm not going to be able to get every single number out as an answer. If you look at the graph, it doesn't go down and up forever. There's a floor to the bottom of the graph. It never actually makes it past negative 4. That's the lowest value that it can ever achieve. There's nothing below that. Now up above, it does continue forever, and so I can get really, really big answers. but I'll never get like -10. That's an impossible answer because it only goes down to -4. So the range or the y values would be from -4 to positive infinity. And mathematicians put a bracket on that -4 because we can actually equal that output. That happens at an x value of -2. So just like how we checked a couple of points, if you put -2 in, you would get that output of -4, and that's why we have a solid point there. We can stand there. Hopefully this first page kind of introduces you to this idea. We're going to start building up layers of transformations on top of this absolute value pattern. So let's flip to the back. On the back, with question number 5, I have r of x. Now, good old Ronald here is equal to negative, and then x minus 3 inside absolute value bars, plus 8 afterwards. So some of the transformations here, that negative is a reflection, the minus 3 inside is shifting it right 3, and the plus 8 is shifting it up 8. So that vertex point, not going to be impacted by the reflection. It's the one spot because it's at a height of 0, negative times 0 essentially does nothing. But the right 3 and up 8 drags that vertex point to its new starting spot. Now everything else is impacted by that negative. Now think about absolute values and the parent graph pattern. Typically it's 1 over 1 over 1 over 1. But here, because of the negative, it's -1 over 1, -1 over 1, -1 over 1. You take it from being positive to being negative. Down 1 over 1, down 1 over 1. And that's going to be on both sides. If you extend the graph all the way out, it definitely looks like it's been reflected. It's hanging out upside down. So what is our domain and our range? Well, the x values, where it goes left and right, this graph never stops. Essentially, you can choose any x values and they're all going to work in the equation. There are no duds. The y values, or the answers that you would get out, are shown by the heights. Now this graph is going down forever and ever, so it's coming from -infinity. It does not go up forever though. There is a ceiling to this function, and that ceiling happens at 8. So I'll never get an answer of 9. I'll never get an answer of 10. Those are impossible answers. The math just doesn't work to ever get those. Even an answer of 8.1 or 8.01 is impossible. 8 is the very last value I'm ever able to achieve, and so that's why my range is from -infinity to 8 with a bracket on the 8. If you're still struggling with range or even domain, hopefully these questions are going to get you a little bit more practice and you'll feel a little bit more comfortable. Number 6, w of x equals 2, and then we have the absolute value of x. Afterwards is -1. So the 2 is a stretch. It's going to make it twice as tall in the vertical direction. The -1 at the end is shifting it down 1. So that vertex point shifts down 1, and then all the other points of each arm are stretched to be twice as tall. So instead of a 1 over 1 pattern, the slope of each arm is 2 over 1. It doubles the height. So 2 over 1, 2 over 1, 2 over 1, 2 over 1. Essentially, any whole number in front of an absolute value, you can divide by 1, and it gives you the rise over run pattern. So 2, or 2 over 1, is your slope. If you look at the domain, the x values, it goes left and right forever, which I hope that you're picking up on a pattern. All absolute value functions can use any number that they want. They have the whole buffet, from negative to positive infinity. Everything works. The range, though, is limited, and so from here, the floor is at -1, and it goes up and up forever to infinity. So -1 with a bracket to infinity, and infinities always have parentheses because you can't catch them. You can never equal infinity. That would be ridiculous. So here with question number 7, we have y equals, so just kind of a regular equation. We have 1/3 in front, the absolute value of x plus 2, and then plus 1 is after the absolute value bars. So in this case, the 1/3 is compressing our graph towards the x-axis. So it's squishing it towards the middle. The plus 2 is shifting it left 2, and then the plus 1 is up 1. So if we go ahead and move our vertex, left 2 and up 1, it's not really impacted by the compression. The vertex point behaves pretty nicely. The arms, however, instead of being a 1 over 1 over 1 pattern, you know, this kind of like regular V shape, it's squished down, it's compressed like a soda can. And so the slope here is 1 over 3, up 1 over 3, up 1 over 3. You could also go up 1/3 of a box and over 1. up a third of a box and over 1, and then if you go up another third of a box and over 1, you land on a nice whole point. And so you can take itty-bitty steps, or you can take larger steps in terms of 1 box, 3 box, 1 box, 3 box. Both of those patterns are correct patterns. It's just proportion or size of your steps. The domain for this graph is negative to positive infinity. Everything works. And then the range, it doesn't go down and up forever. The floor is at positive 1. So from 1 to infinity, that's where the graph is, and those are the answers that we're able to get out. We'll never get an answer of 0, unfortunately. And we'll never ever get an answer that is negative. The last graphing question, number 8, says d of x equals -4, and then the absolute value of x minus 5. All that is inside. The negative is a reflection across the x-axis. It'll be upside down, like an A. The 4 is stretching it, so it's 4 times as tall. This is a vertical stretch. The minus 5, which is inside, is just moving it right 5. So we'll do that transformation first. That vertex point, the negative doesn't impact it, the 4 doesn't impact it. It just stays where it got moved, left and right, up or down. Then we'll go ahead and we'll look at the slope. Instead of being 1 over 1 over 1, it's upside down. And instead of being down 1 over 1, down 1 over 1, it gets stretched away from the x-axis to be down 4 over 1, down 4 over 1, down 4 over 1, down 4 over 1. Both arms are like that. And I know we can't get a lot of dots in, but get as many dots as possible so that we have the clearest picture in the space that we're provided. The domain of this function is from negative infinity to positive infinity, and the range is from negative infinity, since it's going down forever, all the way up to 0. That is the last height that I'm able to achieve. 9 and 10 are kind of specialty questions where we ask you to do this idea a little bit backwards. So you definitely can graph them, but can you go from some other information to the original equation? That's what we're looking for. So can we write the equation for an absolute value function where it's been dilated by 3, translated vertically down 5, and then we're going to graph this off to the right-hand side. So starting off, we need something equals. It can be y equals, it can be g of x equals, it can be any name equals. But if you don't have an equal sign, you aren't writing an equation. Very important. Now, after we have the equals and the name, we're going to start off with a 3, and that's that dilation. Specifically, this is stretching it to be triple height. After the 3, we put the absolute value of x, and sometimes I leave space in here in case I need any horizontal movements. But since this problem doesn't have anything like that, I can keep the absolute value bars close to the x. After those absolute value bars, because I am shifting it down 5, I'm going to put a minus 5. And that's your equation. Taking that and graphing it should be pretty simple because we have a lot of experience with that now. So I'm going to go down 5, that's where the vertex is, and then the slope of this v is up 3 over 1, up 3 over 1, up 3 over 1. It's been tripled or stretched out in the vertical direction. Do that on both sides, and you're done. Pretty quick. The very last problem, problem number 10, asks us to look at this graph and write an equation. So we have to tear it apart and we have to deconstruct it to look at some of its qualities. If we're wondering where it definitely went left 3 and down 2. Those are numbers that are going to be inside of our equation in different spots. In terms of the pattern, it looks like it's been squished down. And so that's a compression. Think about numbers that would compress your graph. If we're going to write the equation, we have to start off with something equals. So we'll just start off with y equals. Pretty easy. Now the compression part that I just mentioned, well, what is the pattern of rise over run, rise over run? If you're counting boxes, it's 1 over 4. Now if you put 4, that's not the same slope. That's a stretch slope. We need a compressed slope. So 1/4 in front, then we have absolute value bars, and we need some space inside because along with x, we're going to be putting a plus 3. That's the left 3 movement we just mentioned. After those absolute value bars, minus 2 takes the whole graph and it shifts it down to right where the vertex was. Hopefully these questions explain how absolute value functions behave and what qualities they take on if they're transformed in different spots. Great job on hanging along with me as we really dove into our first function of the year. We'll get more experience with other types of animals as we go, and by the end of the year, you're going to be like a zookeeper of all these math functions. It's going to be great. So thanks for watching this video, guys, and we'll see you in the next one. Take care.